Hello, welcome. Today I'm going to talk about sequences. And sequences are super important. Whenever there's a pattern, there's usually numbers involved, and you can see a sequence of numbers. Later on in your mm, classes, you might consider sequences of vectors, of functions, and whenever you're looking at patterns, usually you definitely need to think about sequences and their properties. In this learning objective, we're just going to consider the basics and focus on these four criteria. First, I can use the exact formula or recurrence relation of a sequence to list its terms. That's, for example, in first sample question here, you're given the exact formula, you need to list down the terms, or here on the third one, you're given the recurrence relation and you need to list the terms. Sometimes you're just given the terms, like in the second sample question, and you need to figure out either the recurrence relation and the exact formula or both. Um, so that's the second bullet. I can find the exact formula and or recurrence relation of a sequence. The third bullet there says I can recognize and analyze arithmetic and geometric sequences. So the main focus here will be on arithmetic and geometric sequences. Otherwise, there are so many sequences out there, and I can create some pattern that it's going to be very hard for you to figure out what's the next term of the sequence or what the pattern is. So this could be very hard, but we're mostly going to focus on these two type of sequences. That does not mean, though, that every sequence that I give you will either be arithmetic or geometric. It could be neither. For example, I could have, say, the numerators of a sequence be geometric and the denominators be arithmetic. You should still be able to find the exact formula for this sequence, but the whole sequence itself generally might not be neither arithmetic nor geometric. So you need to understand and know what arithmetic and geometric sequences are and how to recognize them. Um, and then I can determine if a sequence is monotonic or not, and bounded or unbounded. So when is the trend of the sequence going in the same direction? That's what monotonic means. It could be um, increasing, decreasing. It could be constant. It could be constant in the beginning and then increasing, constant and decreasing. And then that all those are examples of monotonic sequences. Bounded means that it needs to have an upper bound and a lower bound. Just because it has one, that does not make it bounded. Whenever we refer to bounded, it needs to have both. And here you need to really be careful whenever you're looking at these two properties, because you're analyzing a sequence of dots, not the underlying function. So you could have, for example, a sequence be described by a polynomial like n squared, and then that would look like a parabola. However, the sequence will be just dots on this parabola. Okay, so you have to be very careful here that you're not confusing, is the sequence of dots monotonic? Is the sequence of dots bounded or unbounded? It might happen that the function you're given, the underlying function, is not bounded. It has a vertical asymptote, for example, but the underlying sequence, is does not is still bounded because it skips over that asymptote. It's a sequence of dots. So you have to be careful to compare and contrast the two here. Um, so let's do a quick example here. We're going to do this one question here. Consider this sequence where we're calling the first term a sub 1. Write down the next two terms in the sequence and find the recurrence relation describing it. So we'd first write down the sequence, okay? And then we need to find the next two terms in the sequence. How in the world do we figure that out? Well, notice here that the numerators are uh, even numbers, and it looks like we're just multiplying by 2s, and then the denominators we're multiplying by 3s. So and then also the sign is flipping, negative and positive. So it makes sense that in general the whole term we're multiplying by negative 2/3. And if you test it out, that really works out. So hey, we got a purely geometric sequence here. We're only asked for the next two terms here. So after 1681, we multiply by negative 2/3. The top becomes 32. The bottom gets multiplied by a 3. I didn't compute this. I don't really care about this kind of computations. As long as I can see the work here, you don't have to waste your time plugging this into a calculator. Same goes for the next term here. This is 64, and then multiply by another 3. So 3 times 3 is 9 times 81. Okay, now how about the recurrence relation? Well, each term you get it by multiplying the previous term by negative 2/3, and that's what this is saying. Notice here that we're starting at a sub 1, so the lowest index here, n minus 1, has to be at least 1, which means n has to be at least 2, so 2 minus 1 is 1. You can not n equal 1, because that would give me a sub 0 here, but I don't have an a sub 0 term in my sequence. And another thing that you need to mention when you write the recurrence relation, and I forgot to put in here, is that the initial term, so a sub 1 is negative 2/3. You need that because if you don't have an initial term and you give me the recurrence relation, you could have many sequences that start off at different points and continue in a different, very differently than what it was intended. Okay, now I didn't ask for the exact formula here, but if I did, then you could still figure that out. One way to do that is to notice here, okay, what is the fourth term on this sequence? Well, we start with a sub 1 and we keep multiplying by negative 2/3 3 times to get to a sub 4. If I'm looking at a sub 5, well, I'll have to multiply by negative 2/3 one more time. In general, the pattern is that you're starting with a sub 1 and you're multiplying by the common ratio to the exponent here, 1 less than the index. So to get to this term, we're going to step 3 times, multiply 3 times by negative 2/3. So in general, that should be the exact formula is a sub n should be a sub 1 times the ratio to the n minus 1. And another way to look at this more algebraically is think about the recursion here. An is an minus 1 times negative 2/3, an minus 2 times, and a sub n minus 1 itself is, maybe it's best to put in here, a sub n minus 1 itself is a sub n minus 2 times negative 2/3, the previous term times negative 2/3. And so we have negative 2/3 squared now. And then you keep going like that, you get a sub n minus 3, and the exponent goes up by 1. So the index here goes down by 1, the exponent goes up by 1. So the sum of the two is always n. Right? N minus 2 times 2 is n, n minus 3 plus 3 is n. So in general, if we keep going all the way down to a sub 1, we're going to get the ratio here, negative 2/3 to the n minus 1 power. And so a sub 1 is negative 2/3, so that just adds one more factor here, and we get this is the exact formula. I didn't ask for this, but it is useful nonetheless to have that, as we'll see here down below. So is this an arithmetic sequence? We can subtract the first two terms, and we notice that, well, the subtraction of the first two terms is a positive number, whereas the next two terms, it's a negative number, so no, definitely they cannot be equal to each other, so it's not arithmetic. Is it geometric? Well, yes, that's how we figured it out. A sub n divided by a sub n minus 1 is a constant, so a negative 2/3, so yes. is it bounded? How do we find if a sequence is bounded or not? The first thing I would do is go to Desmos, and so go to Desmos here, and we can plug in a of x is negative 2/3 to the x power, make a table. You can click this plus button on Desmos and click table, and then modify what's the y here. And that should give you the terms. And the nice thing is that if once you do a few terms, to go to the next one, you just press enter, automatically gives you 12 and then 13 and so on. And it makes all the calculations for you. You can also put in a point in here so you can kind of see in a slider. Once you put in the point, they will give you the option for a slider. And I wrote it in terms of n. And this kind of makes this point dot move between all the different points, as you can see here. Click on this to change the way the animation goes, if you want to keep all the start to the left and go forward or not. And so that's helpful in terms of using Desmos. And we can see that the sequence here is oscillating and tending towards 0. Is it bounded? Yes. Is it monotonic? No, because it kind of bounces up and down. But we need to argue that somehow mathematically. And one way to do that is to look at whenever you want to bound the sequence, it's the same thing as bounding the absolute value of the sequence. Okay, so looking at the absolute value, it is equal to 2/3 times the absolute value of the previous term. But that 2/3 is less than 1. So this 2/3 times whatever this previous term is less than the previous term itself. And repeating the same argument, every time you're multiplying by 2/3, it's like taking 66% of what you had before. And so if you go back in time in this sequence, you're always going to get a bigger number. And all the way going back to a sub 1 in absolute value, that's 2/3. So we have a sub n is in absolute value less than 2/3, which means a sub n is between negative 2/3 and 2/3. That doesn't mean that this is true. It must be the lowest possible lower bound. So notice here that this is negative 2/3, but the upper bound here, it is not 2/3. It's a little bit smaller than that. That is okay. We don't care to be exact here. We just want to be bounded. Do I have the lowest possible upper bound? No, it doesn't matter. I could also use the exact formula here to argue. Negative 2/3 to the n is bounded by 2/3 to the n and negative 2/3 to the n. But then each of these, you're just keep multiplying, so they get smaller. So you can, if you make the exponent 1, that is going to be a bigger number. And so here, because this is negative, that will make it a negative number. And so we have that a sub n, which is this middle term, is between negative 2/3 and 2/3. And so yes, it is bounded. Is it alternatively, you could also take the limit and see that the limit is 0, use the squeeze theorem here to say that why the limit is 0. And we know that if a sequence is convergent, then it must be bounded. So that's another way to think about it. And monotonic, you can definitely see A1 is less than A2, but A2 is bigger than A3, so it's not monotonic. And so we're done. And that's it for this video. Thank you for watching.